In the last couple of videos, I've introduced you to the static friction force. The static friction force acts when there is not yet sliding motion between two objects with surfaces in contact. The static friction force tries to keep that sliding motion from ever getting started in the first place. In this example, we have a finger which is pushing a mass into a wall. We are given the mass, 4 kilograms. We are given the strength of that push, 29 newtons. And also we're told that the push force is directed at a 60-degree angle above the horizontal. We're also told that the mass does not slip. And so we want to find the strength and the direction of the static friction force acting between the mass and the wall. So we're going to solve this problem using the first condition of equilibrium. And as with some of the previous videos, we're going to be using this handout here to guide us through the application of the first condition of equilibrium. All right, so step 1 says draw a sketch of the problem. Here's a sketch. Step 2, select an object from your sketch and draw a dotted line around the sketch. So the object we're going to analyze here is the mass. So I'm going to draw a dashed line around the mass. That's step 2A. So step 2B says draw in the gravitational force vector acting on the object. So I'm going to make a clean figure over here. And I'll start by drawing in the gravitational force vector pointing down. Step 2C says go around the dashed line and note any locations where the dashed line makes contact with the object surroundings. So we're going to go around the dashed line and see where other things might be reaching in through the dashed line to exert forces on the object. So if I start down here and start to go around the dashed line, I can see the finger reaching in through the dashed line to exert a force on the mass. And the force exerted by that finger is already drawn into the figure. That's the push force there. So I'm going to go into the figure and in that push force. Okay, and let me also indicate the direction here. It is 60 degrees above the horizontal. Okay, now the other thing we see reaching in through the dashed line to contact the mass is the wall itself. Now, the wall will exert a normal force on the mass. So that normal force that the wall exerts on the mass will be pushing out to the left. Okay. And then finally, we have the static friction force. Now, a frictional force has to be exerted parallel to the surface exerting it. Now, the wall is vertical, so we need to have the static frictional force pointing in a vertical direction. However, there are two possible vertical directions. One possibility is that the static friction force is pointing up along the wall, and the other possibility is that the static friction force is pointing down along the wall. Now, why would both of these be possibilities? Well, suppose, for example, that this push here is very, very hard. If this was a very strong push, the tendency would be for that mass to slip up the wall. And if the tendency was for the mass to slip up the wall, static friction would try to hold things in place by pointing down the wall. On the other hand, if this was a very light, weak push, imagine someone coming in just with their pinky and pushing as light as possible, then the mass would tend to slip down the wall, and then friction would try and hold things in place by pointing up the wall. And at this point in the problem, we don't know which it is, so we have to guess, and I'm going to guess that the static friction force is pointing up the wall. Okay, so what happens if I'm right? Well, if I'm right, we're going to solve for the magnitude of the static friction force, and it's going to come out to be positive, and then we're done. On the other hand, if I'm wrong, and in fact the static friction force is pointing down the wall, then the magnitude of the static friction force is going to come out to be negative. For example, suppose that what's really going on is that there is a 10 Newton static frictional force pointing downward. If in reality there is a 10 Newton static friction force pointing downward, but I put the static friction force in my diagram pointing upward, then I will get the result that Fs equals minus 10 Newtons. And I'll say, all right, that's okay. I just need to flip the static friction force over and reverse the sign. Okay. So if you're doing your homework problems and you have to make a guess like this, and the magnitude comes out negative, no big deal. It just means that you initially had your force pointing in the wrong direction. So at the end of the problem, just add a notation that in fact that force is pointing the other way, and here's the magnitude. Okay, anyways, let's proceed with the steps on the handout. So we've gone through step 2C. Next is step 2D, which says label each vector. And I have already labeled each of those vectors with vector symbols. Now I'm going to go in and put in the magnitudes. So for the magnitude of the gravitational force, I'm going to put in mg. For the magnitude of the normal force, n. For the magnitude of the push force, p. Now for the static friction force, you saw in a previous video that if the static friction force is maxed out, then we write the magnitude of the static friction force as μs times the magnitude of the normal force. However, in this problem, there is nothing telling us that the static friction force is actually maxed out. So we are not going to say that Fs is equal to μs times n. What I'm going to do instead is just write in the magnitude of the static friction force as a generic expression, F sub s. Okay, so that's step 2 on the handout. So step 3 says introduce a Cartesian coordinate system. And remember, we want to introduce Cartesian axes that align with as many of the vectors as possible. Now here, can you see that if I use standard orientation with the x-axis pointing right and the y-axis pointing up, then my axes align with the 3 of the 4 vectors, static friction, gravity, and normal force. So this is the clear choice. Okay, so I'm going to go in and put in x and y axes. Okay, so x to the right, y up. Now, at this point, if you like, and this would be optional, you can draw the axes again, and then just shift all of those vectors so that the tails of the vectors are at the origin. That makes it a little easier to see what's going on with all of those vectors. So this step is optional, and you only need to do this if you think it would be helpful in order to see the vectors on the axes more clearly. And 60 degrees in here. Okay, so now we can go to the grid. Okay, now we can go to the grid. So as usual, start by listing the vectors across the top. We have gravitational force, push force, static friction, normal force, x component, y component, Okay, so we'll go through, put in the components. The gravity is pointing along the minus y direction. So the x component is 0, and the y component is the magnitude, minus mg. So that p vector, if you look at the projection onto the x-axis, that would be the magnitude times cosine 60. So p cosine 60. And if you look at the projection onto the y-axis here, that would be the magnitude times sine 60. Okay, we have static friction force pointing along the plus y direction. So the x component is 0, and the y component is Fs. You have the normal force pointing along the minus x direction. So the y component is 0, and the x component is minus n. Okay, so going back to the sheet, we've just done step 4. Now we go to step 5, which is to plug our results into the first condition of equilibrium. And if you think about what we're trying to do here, we're trying to solve for the magnitude of the static friction force. Now, if you look at all the y components of all the forces, all of these quantities appearing in this bottom row here are known, except for the magnitude of the static friction force. So we don't actually need the x equation in this problem. We just need the y equation. So I'm going to write that the sum of the y components of the forces is 0. And now sum along that bottom row, minus mg plus p sine 60 plus fs equals 0. Okay, so now just take those two terms there and move them to the right side where the signs reverse. And then I get magnitude of static friction force equals mg minus p sine 60. And now I make the substitutions, mg, so that's 4 kilograms times 9.8 meters per second squared, and minus 29 newtons, sine 60. Okay, so notice that kilograms times meters per second squared is newtons. So both terms have units of newtons, which is what we want. And when you substitute into your calculator, I hope you get 14.1 newtons.